Let's add a bit more to this 10 to 20 day and 30 to 60 day interseasonal variability and their propagation regionally over the Indian Ocean onto the subcontinent. We already said that the spatial scales of the 10 to 20 day mode is much smaller than the 30 to 60 day mode, which is extending all the way from the tropical Pacific into northwest India, right? So this is just the lag latitude section of regressed anomalies of 30 to 60 day filtered 850 hectopascal relative vorticity, which we had just seen for the propagation in the previous figure here, right? This is with respect to the same time series used before. It's averaged over 80 east to 90 east, so it still remains predominantly on the Bay of Bengal. That's where the most active northward propagation happens, and then you get the low pressure systems and monsoon depressions bringing moisture into the core monsoon zone, in addition to the mean circulation from the southwesterlies and the backflow from the Bay of Bengal. Just keep that in mind. I keep saying that because even though we keep talking about monsoon interseasonal oscillations, their relation to active break periods, the spatial propagation is much more prominent over the Bay of Bengal. Lag longitude section is shown here of the regressed anomalies of 30 to 60 day, same thing, 850 hectopascal relative vorticity. And what you can see here is that when you look at 80 to 90 degree east averaged longitudinal band averaged northward propagation, you see the clear origin of these. Again, we are doing the lag lead kind of half-Muller plot where day 0 is when the precipitation is maximum over the Bay of Bengal. So you can see here this is starting in the tropical band. I will come back to this in a minute. Mostly in the central eastern Indian Ocean. The west, as we saw before, the cross-equatorial flow, the Somali upwelling and so on, creates a almost a break in the ITCZ, which we will see again. Okay, so you can see the break and active period. So this is the active period here. Sorry, let's make sure. So day 0, that's the active period there over the northern Bay of Bengal, and you can see, so just make sure the vorticity sign you got right. So cyclonic motion, counterclockwise motion, vorticity direction is positive Z, right? So you can see this genesis happens here. There are details which we will get back to when we do the mechanisms, and there is northward propagation. You can figure out the propagation speed, but there is year-to-year variability, decade-to-decade variability. Within the season there are variabilities of these features, so this is kind of a composite, so you have to be careful anyways. And then you get the next phase, and so on. And if you look at the latitude averaged zonal propagation feature, so this is the lag longitude section with respect to the same reference time series. This one is average 10 north to 20 north, so from the peninsular India over to the core monsoon zone. And you can see that there is the these are moving northeastward. So this is the north and this is the eastward. In eastward, propagation is much faster, you would say, because they are covering a large longitude band in a few days compared to here. So there is the northward propagation and there is the eastward propagation, but you again see the negative positive kind of feature, right? The question is, do we know why these things have the scales they have in terms of time and space? As we said, there are many theories, which usually means there is no consensus. So there are several hypotheses that are built based on data, and they are all tested, and some of them fit some features of the mesos, others fit the other features, so you end up having multiple theories. Now, looking the same at the same kind of figure for 10 to 20 day mode, this is averaged at 5 to 15 north, and here 5 to 15 north here, and this is the same latitude band 80 to 90 degree east. And you can see that this is very different, so there is almost like a jump rather than a smooth propagation. Here you can clearly see smooth propagations, whereas you see almost a jump. So the propagation is not always very clear in the northward direction, but the westward propagation, so remember time is going this way, lag minus 15 to lag 15, so you are going from the northwest tropical Pacific, just western Pacific maritime continent towards Bay of Bengal. So the Indian subcontinent is here, Bay of Bengal is here. So there is also a transition from this mode into the low pressure systems and monsoon depressions. Okay, so these are just obviously regressed extractions of filtered signals. But if you look at this animation, which is showing pentad rainfall, when you come to May, June, you can see the ITCZ is trying to move north. As we said before, the ocean is warm, so the ITCZ over the ocean still remains. So in the beginning of the year, it's all to the south. As spring comes and summer commences, you begin to have land heating, monsoon onset, but the equatorial crossing of the ITCZ happens in March, April. But you can see also that the ITCZ almost gets chopped off here because of the upwelling and the cold temperatures, the Findlater jet, alongshore winds, Somali upwelling, and so on. So all the action is over here. We will see later that the convection genesis happens here. There is eastward propagation, so MJOs continue eastward, southward, etc., as we mentioned before, and as we will see again a little bit later on. But the northward propagation and northeastward propagation are all focused on here, so that is something that has to be remembered. Each time I'm saying these things, you may get a sense that we know a lot and yet we don't know a lot, so that is a good opportunity for research. A lot of questions still remain very open, even in terms of the fundamental theories of spatial and temporal scale selections. Okay, so that's something to keep in mind. And to give you a sense, this is a figure from Tim Lee's book on tropical climate dynamics, and it's showing the MISO season and the MJO season. So it's showing standard deviation of the 20 to 80 day filtered precipitation anomalies. So you can see the scale here. So obviously you are seeing the intraseasonal component of the ITCZ, which is to the south in the boreal winter, and gets split and moves north gets split over the Indian subcontinent. But here you get the Indian region, SPCZ, and the ITCZ. The intraseasonal part clearly shows that there is the Pacific East Asian monsoon component and the South Asian East Asian monsoon component. And the vectors here are the precipitation propagation vectors. So you can see here the eastward and northward propagation, whereas here you have mostly eastward and southward propagation. So why is the year split into these May to October, December to April seasons? Obviously has something to do with the sun moving and the ITCZ. And the northward propagation here, again, the eastward propagation is common in both seasons, so a lot of genesis of convection happens here in the western Indian Ocean throughout the year, and something detours the eastward propagating systems northward in the summer season, boreal summer season, whereas they continue eastward or southward in the MJO season. Okay, and you have this direction here, which is related to our 10 to 20 day systems coming from here, and the large scale tilting structure that we see also with the 30 to 60 day band, right? So these are kind of questions that remain. And the other question is also, when you look at the active break periods over the Indian region, we said we have 10 to 20 day band and 30 to 60 day band. And if you just eyeball this, you think dry years like 72 and 2002 have more of the 30 to 60 day variability, and a wet or normal year maybe has a 10 to 20 day kind of structure, more of the 10 to 20 day kind of structure, or maybe a mix of 10 to 20 day and 30 to 60 day. And there are some statistical analysis which argue that drought years are consisting of more of the 30 to 60 day. But again, explaining that in terms of the internal variability of the monsoon generating droughts versus external forcing like the El Nino or the Atlantic Nino or the high latitude forcing, they have not been resolved in terms of how they impact the two frequency bands in the intraseasonal time scale. So those are still somewhat open questions, but still they are very interesting questions. This is from Bin Wang's chapter from the same Lau and Walliser book that we'll come back to when we look at the theories of interseasonal variability, but gives you a sense of the complications involved, but also the fact that there are multiple theories, which means we still have some understanding to be advanced. So land sea distribution is obviously important for the monsoon circulation, and you have the land heating and ocean heating and the tropospheric temperature gradient, which just by your thermal wind circulation, thermal wind response would give you the vertical shear. So that it becomes critical. There is SSTs that are supplying water vapor. Boundary layer dynamics are invoked by some theories, frictional convergence, moisture. So moisture, diabatic heating, and waves are critical for almost all of the theories. And things like Vichy, wind-induced surface heat exchange, ocean mixed layer dynamics, which we will look at, feedbacks with cloud radiation, mesosynoptic systems, so you have the 10 to 20 day kind of time scales, and higher frequency 3 to 10 day kind of low frequency low pressure systems as well. These numbers are the processes which we will look at later. So the convective latent heating, and there are low frequency equatorial waves. So we will see that the Kelvin waves and the Rossby waves, which are lower frequencies, Kelvin wave is of course much faster than the Rossby wave, since still they are slower than the synoptic timescales we will consider. So the basic story is that there are lots of things known from data and analytical models and diagnosing full GCMs and so on, but the complete theory of intraseasonal variability is not known. Often we tend to split it into Madden-Julian oscillations and monsoon intraseasonal oscillations, and the two understandings go separately, but the detouring, northward detour of the interseasonal oscillations in boreal summer remains investigated separately as well, in terms of whether it's the vertical shear that is important for energy to generate these waves, so convert potential energy into kinetic energy of the propagation, or is it the meridional shear and the barotropic instability, because the southwesterly jet also has a strong meridional gradient of zonal winds, which is barotropic instability, which also can be converted into eddy kinetic energy and northward propagation. So these questions also remain open. I'm saying these in a very fast way, but you can read the chapters and the various references therein for these details. Okay, so I'll come back with the next section of the Goswami chapter in the next podcast.